Next, let's look at another really important data structure, which is called a heap slash a priority queue. Let's start with kind of the meaning behind priority queue. We already talked about regular queues where first value in is the first value out of the queue. But we might want to order the queue a little bit differently. Instead of ordering it by the first in, first out, we could order it based on some type of priority value. For example, we add some values like 7, 3, 9. So now which value are we going to pop first? Well, it depends on the priority of the values. There's typically two variations of this. One is, the minimum priority and the other is the max. So in this case, we could prioritize the minimum values first. So if we did it like that, we would first want to pop the 3 and then pop the 7 and then pop the 9. Now this is dynamic, meaning as we add values, we might choose to pop a different one. Right now we want to pop the 9 if we pop a next value. But if we add a smaller value, suppose a 4, in that case, we're going to want to pop the 4 first and then pop the 9. That's if we did it based on minimum. Of course, we could do it based on the maximum as well. In that case, we'd do 9 first, then 7, and then 3. So the idea is actually pretty straightforward. Now, the reason we have two different names here is kind of the same idea. When we originally had queues, those queues were actually implemented with linked lists. So in this case, the relationship between these two terms is similar. The interface that we're using is called a priority queue, right? That's kind of the idea behind it. But underneath the hood, that's implemented using a heap. So people kind of use these two terms interchangeably. So you'll see that a lot. I'll probably be doing the same. And outside of this course, people use these generally interchangeably. I think it's more common to use the term heap, just probably because it's shorter, to be honest. But in this case, a priority queue is going to be implemented with a binary heap, which is this data structure that we have here. This is what we're going to talk about. And by the way, that heap, that binary heap, could either be a min heap or a max heap, depending on how we want to implement our priority queue, whether we care about minimums or maximums. I'm mainly going to be focusing on the minimum case. Generally, it's more common to use a min heap rather than a max heap. That's what this is here. But the implementation is pretty much exactly the same. It would just be swapped. It would, instead of taking minimums, we would take the maximums. I'll talk about that more now. Now, at first glance, this looks like a binary tree, and that's because it is a binary tree, but it's not a binary search tree, and you can tell because the root here is 14. With a binary search tree, every value in the right subtree would be larger than 14, which it is in this case, and every value in the left subtree would be smaller than 14, but that's definitely not the case. Actually, when you look at the root node here, it's smaller than every single descendant in the tree. That's going to be the order property that we talk about in a minute, but let's first start with the structure property. A binary heap is essentially a binary tree that is considered a complete binary tree. So a complete binary tree basically means we have a tree where every single level in the tree is going to be completely full. There's not going to be any holes anywhere except possibly the last level. The last level might have some holes, but every other level in the tree is not going to have holes. So you can see that requirement is satisfied in this case. Now, maybe if we're missing this node, it would not be the case because we're supposed to have 4 nodes in this level, but we only have 3. So if any of these 4 nodes is missing, we don't have a complete binary tree. If any of these 2 nodes are missing, we don't have a complete binary tree. Now, the last level here, we can have some missing nodes. That's perfectly okay. But if we insert a node over here now, regardless of the value, tell me, is the structure property satisfied? Definitely not, because while the last level has some missing nodes, that's okay. The second to last level now also has missing nodes. That's definitely not okay. Now, another thing about the structure property, as we add values, you can see they're added left to right. It's not enough that only the last level is allowed to have missing nodes. If it does have missing nodes, they should be at the end of that level, meaning that as we add nodes to it, like assuming that this level doesn't even exist, as we add nodes, we'd first add the node here and then add the node here and then add a node here, then here, then here, then here. So it's kind of intuitive that we want to have a complete binary tree, and as we add nodes, we're adding them in a pretty straightforward way, right? In the next available position, essentially. So that's the structure property. Next is the order property. Remember, the whole point about having this heap, aka priority queue, is about finding either the minimum or the maximum value really quickly, really easily. That's the entire point of having a priority queue. In this case, we're talking about minimums. So it makes sense that we would want the minimum value among all of these to be at the root, because from the priority queue, we want to be able to find the minimum easily. By looking at the root, we can do that pretty quickly. We can look at it in O of 1 time, as long as we're not removing this. So what order property should we give this to do that? Well, we should say recursively for this tree, we want every value in the left subtree to be greater than 14 and every value in the right subtree to also be greater than 14. That's the only requirement we have, but it's recursive. That means that for this subtree, for the root node of this subtree, we want every value in its left subtree to be greater than 19. That is the case, as you can see here. And we want every value in the right subtree to be greater than 19. That's also the case, as you can see here. Same thing for 16. 19 should be greater than 16. It is. 68 should be greater than 16. And technically in heaps, we're actually allowed to have duplicates. You can see we have two 19s. So actually when we look at this value, we don't necessarily need every value in the left and right subtree to be greater than the root node. It's okay if they're equal as well. That wasn't true for binary search trees, but it is true for heaps. We could have some duplicates, and that's okay. It's just that for every node, all the descendants have to be greater than or equal to that node. At least when you're talking about min heaps, which is what we're doing here. Obviously, for a max heap, we would want the opposite. We would want for every node, all of its descendants should be smaller than it, because in that case, we would want the maximum to be the root. Now, one of the most interesting things about binary heaps is that while we draw them as binary trees that are connected via pointers and nodes and all that, they're actually implemented under the hood using arrays. And another interesting thing is that we actually don't start at index 0 for this array. We essentially don't care about the 0th index, and I'll show you why. So what we're going to do is put the root node at index 1. That's always going to be the case. The root is always going to be at index 1. So we got the root node. Next, we fill in the next level. We go left to right. So for the 19, we're going to put it at index 2. For 16, we're going to put it at index 3. And we're just going to continue going like this. But one thing I want to point out is that we know the root is at index 1. To get its left child, we go to index 2. To get its right child, we go to index 3. Let's continue this, and then I'll show you what's the pattern behind it, and then we'll understand exactly why we use arrays rather than nodes and pointers. So filling in the next level, we have 21, which goes at index 4, 26, which goes at index 5, 19, which goes at index 6, and 68, which goes at index 7. And the last couple nodes we have 65 and 30. They're going to go in index 8 and index 9. So the main reason we skip index 0 is to get the math to work out. What do I mean by math? Well, for index 1, to get its left child, we basically have a few formulas. So for any node, so for 14, which is at index 1, to get its left child, we simply take the index that it's at and multiply by 2. So we know that its left child is going to be at index 2, which is 19. That is the case over here. We know its right child is going to be 2 times I plus 1. I in this case is 1, so 2 times that plus 1 is going to be over here. So just the next position over, 16 is its right child. And as we continue, so for 19, we want to get its left child. We multiply by 2, we get 21. That is the case. To get its right child, we multiply by 2 plus 1. That would land us over here. 26 is the right child. Now, these properties, by the way, are only true because we have a complete binary tree, which means every node is filled except possibly the last level. This would not be true for a regular binary tree or a regular binary search tree. That's why we use these for binary heaps, because they're complete binary trees. That's also why we can use this array to represent the binary tree. Because if we had holes and stuff over here, right, like this 26 doesn't exist, then it wouldn't really make any sense to use an array because we just have random holes everywhere using a regular binary tree. But with a binary heap like this one, we're never going to have holes. That's the entire point of having a complete binary tree. And by the way, if we can go from any node, multiply by 2 to get its left child, multiply by 2 plus 1 to get its right child, then from any node, we should also be able to go to its parent, and we can do that by dividing by 2. Now, it's pretty obvious why if we multiply by 2 here to get the child, we can divide by 2 to get to the parent. But why is that also true for the plus 1 case? If we multiply by 2 plus 1, we get to the child. And then if we divide that by 2, we get to the parent. Why is that the case? Well, pretty much because when we divide by 2, we round down. We know that this number is always going to be even. You know, we're multiplying some number by 2, so by definition, it has to be even. We know that this number is always going to be odd because we have an even number and we're adding 1 to it. This is the odd number, 9. When we take this and divide it by 2, we're essentially getting rid of this 2, so we're left with I plus 1, which is also divided by 2, and we know we always round down. Pretty much every language will round down automatically. With Python, you have to use double slashes, but we can still do that. And when you round down, this term is basically eliminated, and then we're left with a single I. That would be the exact same if we took this and divided it by 2. We would just get rid of this. We'd be left with a single I. So when you take 9, divide it by 2, you get 4.5. You can round that down. That leads us back to 4. So for example, if we wanted to, start at this node, we'd start at index 1. Suppose we want to go to the left. We would just take its index, multiply by 2. That would lead us over here in the array. Now, suppose from here, we wanted to actually go right. We would take the index, multiply by 2, which leads us to 4, plus 1, which leads us to 5. Then we'd be here, or here using the tree representation. And from here, maybe we want to go to the left child. So we take the index, multiply by 2. That leads us to 10. That's out of bounds because it's greater than the last index. Therefore, we reach null. So, it basically can be used the exact same as we traverse a regular tree. As long as you have these properties, you can traverse it as if these were pointers. So this is kind of a good introduction to heaps, the structure property, the order, how they're implemented using arrays. Next, we're going to talk about how we can actually insert values into a heap and remove values into a heap while maintaining the structure and the order properties, because that's very important. Without these properties, we don't have a heap anymore.